Okay, let's start class. Before we start it, I just want to mention I sent an announcement through the email last night. I just noticed next Tuesday I have to attend the tenure promotion committee meetings, which is from 9 a.m. to 4 p.m. on Tuesday. So there's no way that I can do the class on next Tuesday. So next Tuesday was scheduled for the presentation. So I just what I'm doing right now. So what I'm planning is I I will pre-record the lecture probably on Monday. So I will post it in the Moodles so you can watch the lecture on Tuesday next Tuesday, and then the presentation will be on Thursday next week and the following Tuesday. That's the week of next. Okay, so I plan to ask all the 7142 students to do the presentation on next Thursday. And then for all the 4142 students to do the presentation on Tuesday, the week of next. But there's one team in the 7142 that has a time conflict because of the master defense. So what I will do is I will send out an email for to the 4142 students to see if we can find any group volunteer to present on Thursday next week. Okay, so we will have 5 groups supposedly to present on Thursday next week, and 4 groups on Tuesday, the week after. Okay, so any questions? And also, some of you send me the email about what you should return. Should we write a report? No, you don't need to write a report. What I only need is you do the presentation, and also you need to send me the PowerPoint or the slides after the presentation. So that's all I need. Okay. Okay. If you don't have any questions, I will talk about 2 case studies. One is the one that I left from the random forest, and the other one that is the case study about the algae to predict the algae concentrations. So this is the random forest example. So this is a image data analysis. Okay, so here the data set is on a sub-area of a seam that consists of 82 times 100 pixels. Okay, so here what we have is, so think about we have 9 pixels in a 3 by 3 square. Okay, so we have 9 pixels, right? 1, 2, 3, 4, 5, 6, 8, 7, 8, 9. Okay, so we have 9 pixels, and we have 4 spectrum bands. We have 4 spectrum bands. So this is an image from the satellite. So it has 4 spectrum bands from the red to the blue. So for each spectrum bands, we have these readings for each of the 9 pixels. So we have 4 times 9 variables. So that will be 36 predictors, right? So we have 4 spectrum bands and the 9 pixels, okay? And what we want to predict is the soil type or the land type in the central pixel. So that's the response. So we have a few classes. So here you can see the type is we have the central pixel is the red soil or the cotton crop or the gray soil or damp gray soil or vegetation stubble or the very damp gray soil. So these are the classes in the data. So this is not an easy classification task because you can see these are the soil type and the and vegetation, and some of the soil types are very similar. They are like the gray soil. It has three types of gray soil: damp and very damp and gray soil. Okay, so we need to predict these classes through these 9 pixel readings, although the class for the response is the central one. Okay, so this is the data set. So we have 36, okay, predictors. And all these predictors are numeric. So, okay, so let's see. So first, and by the way, this data set is in the ML Bench library. And this data set's name is called the satellite. And if you want to know more details, you can just read the help menu, okay? So there are 36 predictors, and the last one is the response. Okay, so here, I first randomly split the data into training and test. Okay, so I use 4,000, randomly selected 4,000 subjects or rows as the training set and the rest as the test set. Okay, so then I run the random forest. I set the random seed so that I can make the results reproducible. Okay, so that's sometimes is very important, especially when you want to reproduce the results and submit to the journals for the publications. So you definitely need the results to be reproducible. So here in the line you you can see the model is fitted in based on the training set, but also there's arguments about the X test and Y test. So X test is the predictors for the test set, and the Y test is the label for the test data. So the model is trained on the training set, but then do the prediction on the test set. And then here I set the number of trees to be 200. Okay, so by default it will be 500. So let's see. So this is the out of bag estimate for the error rate. So this is just like the cross validation. Okay, and this is entirely based on the training set, not using the test set. Okay, and this shows the confusion matrix. Okay, and you can see the out of bag estimate for the error rate is about 9%. Okay, and then let's see the test set. Since we provide the test, and these are not required, but here I just provide it here, so it will show you the test error. If you don't provide the X test and Y test, it will not show you the test error. Okay, so here since I provided, it shows the test error is about 8.38. Okay, and these are the confusion matrix, and this is the class misclassification error for each of the uh, categories. And you can see here, what are those categories that are easy class to be classified? So you can see like a red, red soil, cotton crops, and gray soil. So these are the 3 types that are having very low misclassification rate, right? You can see they are error is less than 5%. But however, when you look at the damp gray soil, this has a very high. It's about 1/3 of chance to be misclassified. So misclassification rate is very high. Okay, and then let's see the damp gray soil are confused, usually misclassified with what? So if you look at the damp gray soil, like here, we see this is the correctly classified, right? And this is the misclassified, that's 40. And also you can see here we have 40. So you can see the damp gray soil are misclassified by mainly from where? From misclassified as the gray soil as well as the, the very damp gray soil. So these are, so that's why the damp gray soil has a very high misclassification rate because of its it's close to the damp, a very damp gray soil and a gray soil. And also the very damp gray soil has quite high, and the vegetation stubble also has quite high. So you can see different class, they have different class misclassification errors. And this is the error rate. So you can see here, the, the blue ones on the top is the gray soil, right? And the bottom one is the red soil, which has the lowest. And the other class are somewhere between. And why there's a curve? Because the x-axis shows the number of trees in the random forest, okay? And the vertical axis shows the test error conditioned on different number of trees. So you can see the number of trees that we really need is about what? I would say, look at these curves. So they basically got stabilized, I would say, close to 100 trees, right? So after 100 trees, you can see the error curve. They are very stable. So, but before, if we have fewer than 100 trees, you can see we have some fluctuations for some of the categories. So I would say in this case, probably 100 trees is good enough. Okay. Okay, then let's see the variable importance. So in the R, in the random forest, we can easily get the variable importance here through the VAR-IMP, that's variable importance plot. So just using this function, it will show you the variable importance, relative variable importance. And here I set the sort equals to true. So it will show you in the decreasing order. So the top ones are the most important. So you can see the X18, X17, X20, these are the most important, and then goes down. So here I'm using the mean decrease in Gini index. That's the classic one. That is based on the variable improvement for each split, not based on the auto bag approach. Okay, and then so here, so since the X18, 17, 20, these are the three most important. Does that really mean something? So here, in each line of the data, 4 spectrum for the top left pixel are given the first, followed by the 4 spectrum value for the top middle one, and then up to the until to the then top right, and then so on. So we have 36 predictors, right? And that is from 4 spectral band times 9 pixels, right? And this, so the order for the variables are from where? So the first 4 variables, like so x1 through x4, these are the 4 top left pixel readings from the 4 spectrum. Okay, then followed by the x5 to 8. So these are the x5 to 8 are the 4 pixel readings from the top middle one. And then 9 through 12, that's this one. Okay, and then 13 to what? To 16, right? Then 17 to what? 17 to 20. Is that right? So now you can see x17 to x20. These corresponds to what? To the 4 spectrum readings in the central pixel, right? So we have x17, 18, 19, 20. These are the 4 corresponds to the central. And what is the response variable? The response variable is the category that corresponds to the central pixel. So that does make sense. You see that? That is, we interpret why x, so the most important variables are, are the x18, 17, 20, because these are corresponds to the central ones, right? And you may ask, why x19 doesn't appear here? X19 is quite low here. So that probably indicate that for this spectrum, so we have 4 spectrum band, right? Probably the X19 spectrum band is not that important or not that useful to identify the class status. Okay, but for the X18, 17, 20, these are the 3 most important, and that they are all correspond to the central. Okay, so this is the interpretation for why these 3 are most important. Okay, then after we identify these are important, then what is our next step? Our next step is to see what is their impact on the response, right? But don't forget, this is a classification problem. And also, we have multiple class. We have more than 2 class, right? So you say the impact on the response. Since the response variable has multiple classes, we do need to specify the impact on which category. So you need to specify the categories if it's more than 2 class. Okay, so here I will show you some example. Like first one, I plotted the partial dependence plot. Remember the partial dependent plot? That's the plot we can see the marginal effect of a variable on the response. Using the model is fit1, and based on the training set. And which variable do I looking for? I need to look for the x17 because that's one of the most important variable, right? And which class that I'm looking for? That's the red soil. Okay, and the main title for this plot is the PDP. That's the partial dependence plot for the x.17 for the red soil, because that is corresponding to the red soil, not for other types. Okay, and then you can see here, that's the partial dependence plot for the x17 for the red soil. So you can see here when the reading for the x17 decreases or it increases, the likelihood for the sample to be the red soil actually decreases. Does that make sense? So you can see there is a decreasing trend when the X17 reading increases, right? Now, the next one is I'm still looking at the X17, but this time I'm looking at the gray soil. Okay, so it's a different category. Now you can see when the X17 reading increases, the chance or the likelihood for being the gray soil actually increases. So that's why you need to specify which class you are looking for. Because if you don't specify that, it will by default use the first one. Okay, it will use the first one by default. Because when you print the levels, the first one is the red soil. So, but that doesn't mean for all the other category it will be the same impact. No. So you can see as an example, for the gray soil, the X17's impact is totally opposite. Okay, and then I showed another variable, X20. That's also one of the most important variables. But this time I'm still on the red soil. So still red soil, but that's X20. And you can see also it looks different from the X17 for the red soil. For X20, when the reading increases, the likelihood for being the red soil actually increases a lot. So that's why when you plot the partial dependence plot for the categorical response variable, which is the classification case, then don't forget that you need to specify which class you are looking for. And also, you always need to specify the variable. Okay, so this is just showing the density plots for different soils on different variables, just to see. So when we have these results, what is the next step? The next step is you need to verify that, if that is the case, right? Maybe these are just some random effects, may not have a solid evidence to support that. So we need to go back to the data set to check if this is correct, if this agree with the facts or not. Okay, so what we can do is let's first check if X17 on red and gray soil are different. For X17 on red soil, it decreases. From gray soil, it increases. Let's see if that is the case in the real data, right? So here we plotted the X17 on the red and soil two classes, okay? I plotted the density on the X17 readings. So you can see the red soil has the X17 readings are very low compared to the gray soil. You see that? That's the gray soil density. This is the red soil. So that's why so that agree with what we see here. When the reading for the X17 are low, like here, you can see the chance of being the red soil is high because the red soil has the readings mainly in between 50 to 70. Is that right? So between 50 to 70, you can see here it's high. But for the gray soil, the readings are centered around 80 to 100, right? So you can see when it's from 80 to 100, the likelihood for being the gray soil increases. So that partial dependence plot does agree with the facts from the data. Okay, and the next one is to check for the red soil if the X17, X20 behaves differently, and that also agrees. So you can see for the red soil, the X17 has the low reading compared to the X20. So that's why X20 is this shape, X17 is this for the red soil. Okay, so this shows a good example That's how to apply the random forest to the classification problem, especially for those more than two classes. And also, it shows that how you interpret the results, right? First, check the variable importance, then check those partial dependence plot. And don't forget, when you check the partial dependence plot, you need to specify the variable as well as which class you are looking for. Okay, any questions for this? Okay, if you don't have any questions, let's move to the this. So this is a case study of predicting the algae blooms. So the data description. So we have the training set, contains 20 water samples. Each sample is an aggregation of several water samples collected from the same river over a period of 3 months during the same season of the year. And for the test set, it contains 140 independent observations. For this particular data, we have a fixed test and training data. So you don't need to split into training and test. It's already there, okay? And each observation contains 18 variables. So what are these 18 variables? So 3 of them are nominal variables. That means they are the categorical variable. That's the season of the year and the size and the speed of the river. And these are the nominal variables. And then we have the 7 frequency numbers of different harmful algae found in the water. And these 7s are the response variable. So this is an example that we have more than one response variable. We have 7, okay? And these are the 8 remaining numeric predictors. These are the values of 7 or of 8 different chemical parameters measured in the water samples. So how many predictors do we have? We have 3 plus 8. So in total, we have 11 x variables, x, and we have 7 y's. So we have 7 response, okay? And the main goal is to use these 11 x's to predict the algae concentration for these 7 different algae, for these 7 response, okay, on the test set. Okay, so why we need to do that? What's the purpose? And the purpose here, did I? Oh, yeah. So the purpose, I think I skipped. So the purpose is first, all these 7 algae are harmful and constitute a serious ecological problem with a strong impact not only on the river life forms but also on the water qualities. Okay, and being able to monitor and perform an early forecast of algae blooms is very important to improve the quality of the rivers. So that's the motivation and that's the goal. Okay. And the second is the several water samples collected here. This is the location. So these are in different European rivers at different times during a period of a year. And each water sample, different chemical properties are measured, as well as the frequency of occurrence of 7 harmful algae. So why we need to do the prediction? Because here the motivation is the chemical monitoring are very cheap, because for those 8 chemical parameters, they can be measured just within a second. They just like put the equipment into the water, they can measure that immediately. So very easy and very automated. Okay, so they are cheap and easily automated. But the hard way, the gold standard for finding the number of algae in the water samples is actually through very tedious and costly microscopic examination. So for each water sample, it has to be put into the under the microscope to examine that by the technicians, and that takes hours of time to do to find the number of algae from the water samples. Okay, so which is very expensive and very slow. So if we can have some good models, good predictive models that can accurately predict the algae frequency based on the easily available and automated chemical parameters, that will substantially facilitate the creation of the cheap and automated system that can monitor the harmful algae blooms. So that's the motivation. So that also gives us some better understanding of the factors that influence the algae frequencies. So the purpose also for showing you this case study is when you do the midterm project as well as the final project later on. So you always need to describe the data set and also describe the problem. So what is the goal? What is the motivation behind that? And so so we know that so the purpose is why we collect the data and do this analysis is based on these motivations and also provide the background knowledge, okay, if needed. So so here the main goal is to predict the frequency for these 7 harmful algae for the test samples. So these are the 8 chemical parameters, and I just showed 4 no, the first 6 samples. And this data set is in an R package called DMWR. And this package is not well maintained. So if you download it from R, it's not available. But if you searched online, you can still see that. If you Google the DMWR package, it will show you the link. If you click link, you can download this package easily. Okay, that is from the archive for the R package, but it's not in the most recent uh, R repository. So you have to download it from the archive. But this is a very, very good package. And the reason it's not in the current R package repository is because the author for this, the contributor for this package is doesn't well maintain, because R has its own policy that if you want to keep your package still available for the users, you have to update some things because our versions changes updates quite frequently within a year, but this contributor didn't do that. But it still can be used, and it contains lots of good useful functions. Okay, so this shows the first few samples. So you can see the first 3 variables. These are the categorical variables: season, size of the water, or size of the rivers, and the speed of the water in the rivers, and followed by the 8 chemical parameters. And then the last 7 columns are the algae, 7 harmful algae numbers. Okay, and this is the summary statistics. So in the summary statistics, you can see that some of these X variables, predictors, are very skewed, are actually right skewed. So you can see here, like for the CL, the minimum is 0.22. The first quartile is about 11. The median is about 33. The mean is about 43. And the third quartile is about 57. But what is the maximum? Maximum is close to 400. So you can see that these variables are highly skewed to the right. What is skewed to the right means? So if I plot the histogram, it probably looks like that. So the majority of the data are not that large, but we do observe some extremely large observations on the right side. So that's for the CL. But if you look at other chemical parameters, we see that a lot. Like here, NH4, the maximum is over 24,000, while the third quartile means what? That number, there are 75%, 3/4 of the data have the NH4 readings are less than 226.95. But we do have some samples that has, which is over 200 times as the third quartile. Okay. And also for the response variable, you can see we also observe those right skewed. For the maximum value are much larger than the mean and the third quartile, like here. So this is the situation, okay? So the data itself has some extremely large values for both the x variable and the y variables. Okay, so here, if we see that, should we need to do something? And that really depends. For the linear regressions, usually we can do some like a transformation, like a log transformation. Sometimes it works, but sometimes even using log transformation, it may not work, okay? But here, let's just keep as is and see what is the result looks like. So first, let's see the distribution of the variables. Some of the variables are not skewed, not that skewed, like the pH values. So for the pH values, you can see they are pretty symmetric. Okay, you can see the maximum is 9.7, mean is 8.1, and minimum is 5. So we didn't see any extremely large or small values, right? And when we do the histograms, it looks like a bell-shaped. And this is the QQ plot to see if it is normally distributed or not, and with the confidence band. So this band shows that if the point is outside the band, that may be an indicator that we have some outliers. So here you can see we do see a little bit outside the band on the left side. So that can be seen here. So that indicates we do have some a little bit skewed, but it's not that skewed. Okay, we do see some sample has some quite small values. Okay, but this one definitely is not very skewed. Is okay. 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 So, but if we look at some other variables, you can see this is the box plot, right? And box plots, the bottom one is the minimum. The bottom of the box is Q1, the top is Q3, third quartile. This is the median. And this supposedly to be the maximum value, but here, this is not. The maximum value obviously is this one. And then what does that? That is, so usually we have a rule that is when the number is greater than Q3, that's the third quartile, plus 1.5 of the interquartile range. Interquartile range, that's the difference between the Q3 and the Q1. So in other words, that's the height for this box. So if it's greater than Q3 plus 1.5 times of the interquartile range, that will be regarded as outlier, very large outlier. And on the other hand, if it's less than Q1 minus 1.5 in the quartile range. Okay, so let's say this is the Q1. So if we have the 1.5 in the quartile range, let's say it's here. If we have some readings below that, that's the threshold. Okay, but obviously from the left side, it's bounded by the zero. So it cannot go below zero, right? So if we see some points here, then that means the line that shows here is not the maximum, but Q3 plus 1.5 in the quartile range. Okay, and if it's on the bottom side, then it will be the Q1 minus the 1.5 in the quartile range. And this is a side-by-side plot that shows the relationship between the size of the rivers with the concentration for the OPO4. So you can see when, no, this is not the size of the river. This is the speed of the water flows in the rivers. So it's high speed, low speed, or medium speed. So you can see when we have a high speed, that concentration for the OPO4 is relatively low. But it's medium, it's middle, low water flow speed, then the concentration is relatively high. Okay, so that's how we can see the relationship between a categorical variable and a numeric variable. So we can see that through the side-by-side box plot. Okay, so this is just showing you how you can identify the outliers. So you can identify the outliers through the graphically. So what you can do is like here, I plot the algae data sets for the NH4 variable. Okay, so this is the NH4 readings. And what is the x-axis? X-axis is the ID from the first observation to the 200 observation. We have 200 observation in the training set, right? So these are the ID numbers. So here you can see when we plot the NH4 values, you can see we have some extreme large numbers. It doesn't show the ID number unless if you use the identify that function. If you use the identify that function, the mouse will turn to a cross. And when you move the cross, move the mouse to close to that observation, it will show the ID number. Then you click it, that ID number will be on the plot. So that's how you can just use your mouse to move your mouse to move to highlight the one that has the outlier, and it will show you the ID. So this means the 153rd observation has a very, very large reading on the NH4. That's over 24,000. And compared to the others, it's much, much bigger. Okay, and you can also see, just see what does that looks like. So this is the data. This is the sample that has extremely large NH4 readings. Okay. Okay, then I also showed some, and by the way, you don't have to use these techniques, these type of plots in your project. You can use others. So I'm just doing an illustration to show how to describe the data, how to describe the variables, and how to graphically show the one variables distribution or maybe two variables distribution through different approaches. So this is another approach called the box percentile plot. These plots can supply some more additional information about the universe distribution. And at any height of the width of irregular box, which you will see here, these are the irregular box. So the any height at any height, the width of the irregular box is proportional to the percentile of that up to the 50th percentile. When it's above the 50th percentile, the width is proportional to 100 minus the percentile. Okay, so the width of at any given height is proportional to the percent of the observation that are more extreme in that direction. Okay, so the median, the 25th and 75th percentile are marked with the line segments. Okay, so here the height, the one that I called height here, it should be showed in the vertical ways. Okay, so it should be looks like that. So, and the height is really that. But here, when I show it in the horizontally, so the height is really the x-axis. So x-axis, that's the algae A1. That's the first harmful algae numbers. Okay, that's the height. Okay, so here you can see this is the 25th percentile, that's the Q1, and this is the median, and that's the Q3. Okay, and the width of the box at any height, at any algae. So this shows the proportion that on the extreme direction. So what it means, like here, you can see the shape for the small river algae A1. This is quite short, right? So that means what? So that means, so the 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 numbers of the algae A1s in the small river are very close to each other in the lower half of the data. And you can easily see that in the medium and the large. So that means the median, so the lower 50% of the readings for the algae A1s are very close to each other. You see that? Compared to the upper 50%, which is from the medium to the maximum. So we have long tails on the right side, right? So you can easily see that through the these. And also, just compare across the river size. You can see that the large river, relatively speaking, contains the low values for the algae A1s compared to the medium and the small. So the small one contains the highest. See? So this is how you can see the distributions of the variables and also at different river size levels. And don't forget that it's not just showing the plot. You also need to know how to interpret, okay? Okay, so this is to show things. Here we have, for the numeric data, we have 7 response. That's the 7 Ys. right? And we have 8 numeric x variables, 8 numeric x variables, right? So, and we have 3 others, but these 3, like the season and the river size and the water speed, so these are the categorical. So I didn't show here, but the purpose for showing this one is to see if there is any high correlations among these x variables and the y variables. Okay, so you can see for the x variables, among the x variables, so these shows the 8 numeric chemical parameters. So we do see some high correlations in these 2 pairs. And by the way, the blue one corresponds to the positive correlation. The red one corresponds to the negative correlation. And the darkness is proportional to the absolute size. So when we see the dark blue, that means we have a large positive correlations. So you can see the PO4 is highly positively correlated with PO4 or highly correlated with OPO4, right? And for the NH4 is highly positively correlated with the NO3, right? So these are the, but when we look at the response variables, so these shows the correlation among the response variables. And we didn't see any strong correlations. You can see all these, they have the correlation close to 0, right? Because the lightness can easily say that. And also the shape of the eclipse is also showing the how the is proportional to the size of the correlations. And these regions shows the correlation between the x and y's. So these, the one that I put the x here, these regions shows if there's an x variable highly correlated with y variables. And we didn't see that much. But here we do see NO4. That variable seems to be have some intermediate positive correlation with the A6, right? You see that? Okay, so this is, so by showing this correlation matrix can give us some information about the correlation among the x variables, correlation among the y variables, and correlation among the x and y variables. And why I use the shape and the color instead of the number. And the reason is because, so that's also part of things I don't want to see in your presentation, okay, in your PowerPoints, is if you present some table in the presentation, that's fine. But what is not okay, which is really not good, so is that if you include some tables that full of numbers. Think about when you do a presentation, I show you a table with 100 numbers in that table. And I will just talk 1 minute on this slide, how much information you will get from this table with over 100 numbers. You cannot get much because when we look at these numbers, we will get lost, easily get lost, right? But when you look at these, visualize these correlations through the colors and the shapes, and you can easily see what's going on, right? So that's why I'm showing the correlations through these based on the colors and the shapes. I think that's a good way to give the audience a better understanding. Okay. Okay, so my point here is the reason I show you this is I want you to know that when you write the PowerPoint, for your presentations. You have to consider that from the audience perspective. Okay, so what is the level of the audience? Do they know some statistics? If they don't know any statistics, then you have to prepare your slides that fits for their understanding levels, that matches their understanding levels of the statistics. Okay, if the audience, they know a lot about statistics, so they are the experts, then you create your slides which is can include those technical points and more details. But if the audience have no idea about the statistics or not much knowledge about the area that you presented, then you have to be basic or trying to motivate them to get into that. Okay, and usually we have a 3 minutes rule for the presentation. So the first 3 minutes, that's very important in the presentation. So the first 3 minutes, if the audience like lost interest of listening to that, if you start with those technical things and the the words and the material that you show are very hard for the audience to understand in the first 3 minutes, your presentation will be like not appreciated, not understood, because the first 3 minutes you miss that chance. So the first 3 minutes is the time that you need to motivate the audience to keep listening to your presentations and motivate their interest, and then you can slightly to talk more and more details. Okay, so in in this data set we have some missing values. So there were common strategies of handling the missing values. Okay, so the first one is just remove those samples with missing value. That's the easiest one. But that can be so. So there are some others, but the the question you may have is, so which one is the best? There's no gold standard said, okay, this one is the best. We should use that. No, it really depends on the situations. So this one, the first one, could be the best if the samples that with missing values just a few. Let's say in your data set, only like 2 or 3 observations has missing values. The rest all have the no missing values. Then in that case, of course, you can remove these 2 or 3 cases, right? But what if we have quite many samples have missing values, or our data set is very small? We don't want to lose more data points. So, so then this one doesn't seem to be good, right? So we need to find some other ways. So we can replace the missing value with most frequent values. If it's numeric, we can probably replace by the mean or the median. If it's categorical, we can replace by the mode. The mode is the most frequent categories, right? But can we use that? Sometimes. In the case that's when, for the numeric variable, when we have like a bell-shaped curve, and also we have just few missing values, then that could be a good way. Okay, but we can also do it by replace the missing values through the correlation among the variables. So can we use that? Yes. And when that is in the in the time that if we can find some high correlations among the variables, then we can, if we have, let's say x1 has some missing values, and if we know x1 and x2, they are highly correlated, then if we have some observation has missing value on x1, but they do have information on x2, then we can utilize this high correlation between the x1 and x2 to impute the missing value in the x1 based on the value from the x2. Does that make sense? So that is the situation that we can use that. Okay, and also we can replace the missing value by exploring the similarity between the cases. Okay, so you can see we have 4 strategies, actually more than 4. I only listed 4. There are many other ways. So which one is better? That really depends on the type of the data and the particular situations that you have. Okay, so here for this training set, we have 200 observations. So first is I use an applied function, and then I showed these are the samples that has missing values. So you can see like the 28th observation has 1 missing value, 38th 1, 48th 1, 55th 2 missing values. Okay, and you can see there most of the samples that has missing values only have 1 or 2 missing. However, we do see that there were 2 observations, number 62 and number 199, and these 2 observations, these 2 samples, they have 6 missing values. That's a lot. Why? Because think about here, we only have what? We only have 7 plus 8 plus 3. So we only have 18 variables. And out of these 18, we have 6 of them are missing. That's about 1/3 of the variables are missing. So this tells us what? Probably we should just remove these 2 missing these samples because they have too many missing values. Okay, and in that package DMWR, remember the one that I taught, and here notice this lower and uppercase. Okay, so there is a function called many NAs function that can remove the row numbers if it has more than 20% of the variables has missing value. And of course, there's an option. You can set the threshold. So by default, it's 20%. Okay, so here I'm using the many NAs, algae, 20%, 0.2. Okay, so that means if any observation has over 20% missing values, then this observation will be removed. Okay, so it shows that many, so and then I will just remove these. So this is a very useful function to remove these cases with missing values. So you can see I still use that approach because that works very well for those observations that has too many missing values, right? Okay, so then we can also fill in the missing value with the most frequent, like for this variable, pH levels, we can probably replace by the mean or median. It doesn't matter because when it's symmetric, mean and median are very close. But for this one, this variable is highly skewed to the right. So mean is not good. Why? Because the mean is highly influenced by those outliers. So the mean probably can go here because we have some very large numbers here. But the median is less affected. Median probably is here. So it's better to use the median. Okay, so we can either replace by the median for this variable and the mean for this variable. But here, the median still applies to this one. Why? When it's symmetric, median and mean, they are very close. So takeaway message is for the numeric variable, if you want to replace by the most frequent, for the numeric variable, it's better to just use the median. Because the median works for both situations. Okay, so in the in in this package, there's a function called central imputation. Central imputation is to replace the numeric variable if we have missing value with in a numeric variable, it will be replaced by the median. If it's categorical, it will be replaced by the most frequent. So this function just use, so use the median for the numeric, but for the categorical, use the most frequent. Okay, so you can use this function. Can easily replace the missing value with those. Okay, and also we can replace the missing value with the based on the correlations. So here I'm showing one example. So we have one observation that has missing value on the PO4. You can see we have one. These are the number of missing values for each variable. But look at the PO4, we have one missing value. However, remember for that correlation matrix, look at this. They are highly correlated. So PO4 and OPO4, they are what? Highly correlated, very positively correlated. Is that right? And the correlation is over 0.8, is somewhere should be here. Okay, so very highly correlated. So if we have missing value on the PO4, but we do find a variable which is highly correlated with PO4, how about we can use that information to help us impute, to get a good guess for the PO4 for that missing value. Does that make sense? So that can also be used. So here I'm fitting a simple linear regression using the OPO4 to predict the PO4. You can see that's the intercept, that's the slope. And then we have one missing value, and that's the 28th observation. Okay, and then since we do have the OPO4 readings for this observation, so what I'm doing here is I'm just plugging this formula. That's the intercept, 42, plus the slope times the OPO4 reading for that observation. And that can be used as our guess for the PO4 reading for that observation. Is that clear? So that is another way to impute the missing value. Okay, okay. The last one is we can also fill in the missing value based on its neighbors. Okay, so if the data set contains both nominal and continuous, here. So the rationale behind that is if two water samples are very similar, and you may ask, what does similar mean? Similar means that if all the X variables are very close to each other, okay? Then if one of them have some unknown value in some variable, then there is a high probability that this value is similar to the value of the other sample. So we can use the similar samples information to impute the missing value in another sample, right? So this approach, we need to define the notation or the notion, what is similarity, right? So we can define some way as a similarity, right? So we can, like, how do we define the similarity? We can define the similarity through the distance. If the distance is small, then they are more similar. If the distance is large, that means they are less similar, right? So the distance, we can use the Euclidean distance, or if it's categorical, we can define some distance, or we can use some default way to measure the distance. Okay, so here the two ways that used for the neighborhood values is for the numeric. So after we find those neighborhood, okay, let's say we have one observation, one sample has some missing values, but we find it's 5 neighbors, let's say. They are very close to this observation. But this observation has a missing value on one of the variables, let's say. Then I can use these 5 neighbors information to impute this missing value. Okay, and for the numeric variable, let's say if the missing value is on a numeric variable, what we do is we have 5 numbers, 5 readings for this variable on the neighborhood, right? So we can use the median. Let's say we have it has a missing value on x1, let's say x1. And we have x1 on these 5 neighbors. So let's just use the median of these 5 x1 readings. And take the median and use that to impute the x1. Right? That's one way. And if it's categorical variable, let's say if we don't know the season, then let's just see what is the most frequent season on among these 5 neighbors. If the most frequent season among these 5 neighbors are spring, then we just impute the missing value as spring, right? Use the most frequent. And also we can use the weighted average. And the weight is based on the distance. Okay, so there are a few ways to identify the neighborhoods and also to find out the number and the categories that impute the missing value. So anyway, you don't have to know the exact details. There is a function called the KNN imputation in that package, DMWR. So the K stands for the K nearest, KNN stands for the K nearest neighbor imputation method. And here you can specify the neighborhood size. So here I use the 10 as a neighborhood size to impute the missing value on the algae. Okay, and you can also specify the method like the medians or the weighted average like that. By default, it's the I think by default it's the weighted average, but you can also use the medians. Okay, so there are options. So the reason I showed you these different ways to do the missing value is so that if your project has some missing values, you can consider which approach that you should use so that you can impute these missing values or just remove that. Okay, you can make your own decision. But in the presentations for this group project as well as for the individual project later, you need to justify why you use this approach to remove or impute the missing values. Okay, so not just randomly pick one. So you need to justify your approach. Okay, so after that, let's see. So we need to process the data. So here, I tried 4 predictive models. First one is the simplest, is the linear regressions. You all know that. And the second is the GAN model, generalized additive model. And third one is regression tree. And the last one is random forest. Okay, so the training set, we have the algae. That's the training set. Test set, we have the one that has the separated for the X and the Y's. So the linear regression and the GAN, these 2 approach cannot handle the missing value by itself. Cannot do that. So what I do is I use the KNN imputation to impute the missing value. But before I impute the missing value, I remove the 62 and 199, these 2 observations. Why? Remember, these two observations has too many missing values. Both 62 and 199, they have 6 missing values. Too much missing values. So I just remove them. So then I do the imputations, KNN imputations, and then I also clean the test set, which also has some missing values. For the cart classification tree, classification and the regression tree, it can handle the missing value automatically. So I only need to remove the 62 and 199, these two observations, and then I will not use the KNN imputation. I will just let the cart do its own way, okay, using the surrogate approach to handle the missing values. And random forest can also handle the missing values using the RF impute function. However, it's tricky that this RF impute function cannot impute the missing value in a test set based on the training set. So I posted a new function in the Moodle RF unsuper. So this is the random forest unsupervised approach to impute the missing value. So that can be applied to the training and test to impute the missing value. So if you want to use this, you can easily see that in the Moodle and then use that to impute the missing value on both the training and test. Okay, so anyway, you can see the point that I showed here is different methods. You can use different approach to impute the missing value, right? Okay, now let's see the prediction models. So for the linear models, I use stepwise selection, step AIC, used to select the optimal model that minimized the AIC. For the GAM model, I use the MGCV and to fit the GAM. Remember that can use the generalized cross-validation to select the optimal smoothing for each component. For the regression tree, I used rpart library to grow a tree, to prune a tree based on cross-validation. For the random forest, I used the random forest package, and the default value is used, so the M tree is used. So here you can see for each method, I specify the details, the functions, and how I process, how I fit the prediction model. These are needed. Why? Because when you, let's say, when you write the manuscript and submit to the journals, these should be included either in the manuscript or in the appendix, so that when the reviewer asks you, hey, how do you fit the models? You need to provide these details so that others can know that, okay, you use these to fit the models. And okay, so in the presentations, I also expect you to show some details. I don't need the code, but you need to show that what package and what function do you use and how do you fit the models. Okay. So in order to automatically fit 7 models, so you can do it in the tedious way to fit one for each response, so that here we have 4 methods, right? So we have 4 methods and we have 7 response. So basically you are fitting what? 28 models. So you can do that line by line by yourself, but also you can do it in the more convenient way. So I use a for loop, I use as dot formula and these, so you can take a look, okay? So that can simplify that, and that can fit all these 28 models very quickly, okay? So this is the model evaluation. So these are based on the test data. So I fit the model on the training, then I evaluate on the test set. So here, the top left one shows the RMSE, root mean square error, on the test set for these 4 methods, and on 7 algae, 7 response. And you can see if you look at that, it's not easy for you to see which one is the best or how good the best is, how worse the worst is, right? So this is called the absolute measure because it's just comparing the RMSE. Okay, like for algae A1, you can see this shows the random forest RMSE, and this show the linear regression and so on. Okay, but it's not easy to see the relative performance. So here I'm using another measure called a comparative RMSE. So still using the RMSE, but for these four methods in A1, I choose the smallest one and scale the smallest one to 1. So basically I'm using the best one, the best model, which has the smallest RMSE, and here is the random forest as 1. Okay, so then I scale the other method's performance correspondingly. So what it shows is the comparative RMSE. So the best one you can see is the random forest. That's 1. That's the base, right? So you can see the linear regression model is what? Is about 1.22. So that means what? Linear regression has about 22% higher RMSE compared to the random forest. So you can see we can easily interpret through the comparative RMSE. Does that make sense? So this is more useful, right? And what's the worst one? The worst one is the GAM. GAM is actually 1.30. So that's 30% higher than the random forest. And the card is somewhere between. Okay? And this is the MAE. That's the median absolute error. Okay, and you may ask why I use two different? Because this one is more robust to the outliers, extreme outliers, and this one is more easy to be influenced by the extreme outliers. Okay, this use the median absolute error. Okay, and but this one is using the mean of the uh, squared errors. So that's why this suffers more by the extreme outliers. And remember, in this data set, one of the features for this data set is what? We have those extreme numbers. So I expect maybe there are some outliers are very large or very small. So that's why I tried both. Just make sure that these are good, they are consistent, or I don't want our conclusion to be just influenced by a few outliers. And this is the comparative MAE. And you can easily see that for both approach, the random forest is consistently the best. You can see the random forest is consistently the best in both measures, MAE and RMSE, and also among all the 6 algae, right? So that's the comparison. So when you do your comparisons in your project, I want you to do something like that, okay? So to have some good interpretation and good results and the plots that you can easily see that. And however, we are not stopping here. Why? Because these I'm showing you the minimum value for the predicted value. Okay, I used apply these to find out the minimum value. Look, the first method is the tree. The second method is the GAN. The third is the cart. The last one is the random forest. Look, for the linear regression and the GAN model, we have some predicted number of algae, which is negative. That is a big problem because we are predicting what? The algae counts. How can that go below 0? How? That's not possible, right? But if I look at the minimum value for the predicted value on all 4 methods, you can see for the linear regression and the GAN, they have some negative value. And by the way, these 1 through 7, these are the algae 1 and the algae 2 to the algae 7. And the 4 rows, each row, the first row is the linear models, GAMs, card, and random. So why these two have negative value? Why not random forest and the card? Because the tree and the random forest is also tree based. These numbers are based on the average of the response. So now you can see what is the good thing for the tree. Tree fits the model using the average of the response. It will not extrapolate a lot. But the linear model and the GAN, they can extrapolate a lot. Remember extrapolation? Extrapolation means that when the data is outside the range of the training data, then when we make the prediction, it can be extrapolation. This is extrapolation. And the linear model and the GAN, they suffered from extrapolation problem, while the tree does not, or the tree-based method like random forest does not. So what we should do, we should truncate it, those negative to zero, because to predict as negative number, that is totally meaningless. We should avoid that. So if I change these negative number to zero, look, I actually improve the results by in the RMSE and the MAE. So this is the showing you that after you predict it, you also need to double check if the prediction makes sense or not, especially when the response variable has a limited, has a reasonable range. Okay, like here, the reasonable range, it should be between 0 and to some maximum counts, I don't know. So, but definitely cannot go below 0. But when we have the prediction below 0, we need to handle that. We cannot let it happen. Okay, so this is an example that shows how you do the data mining. So I hope you can that can be helpful for your group project. Any questions? Okay, let's stop here.